The first astronauts to see our home planet from space described it as a precious jewel hanging in an inhospitable void. Of all the countless stars and planets in the universe, Earth is the only place we know of that has the perfect conditions for life. The extraordinary forces contained within the Earth's protective atmosphere interact to create a world of extremes, which allowed life to evolve into millions of diverse forms. Over billions of years, creatures evolved from the oceans that are just beginning to make the leap from the trees to the stars.
Have you ever wondered why this beautiful but fragile planet seems such an ideal place to live? And have you ever thought about how our bodies have developed suitable life support systems to survive here? Whilst up there, space seems such an inhospitable place. And it is. We did not evolve to live there. However, we have already built life support systems that make it possible for us to survive in space for short periods of time, on craft, like the International Space Station.
The ISS is being built 400 kilometers above our heads in an international effort to create a platform for research and future space exploration. Traveling at 28,000 kilometers per hour, it orbits the Earth 16 times every day. An amazing feat, but this is just the beginning.
I've tried for years to do that, never been able to do it.
By 2035, we hope to travel further and put human beings on Mars. But can we recreate the life-supporting properties of Earth to enable us to survive and prosper in space?
I'm a life scientist working for ESA, the European Space Agency, and I'm going to find out how Earth supports life and how our bodies have evolved to live here. I will show you how we at ESA and other international space agencies are developing life support systems that allow us to travel and live in space for long periods of time.
Contact, captured, docking confirmed.
Earth is the only planet that we know of that is capable of sustaining life with only the energy from the sun as an external input. It has liquid water, a breathable atmosphere and plants that convert the energy from the sun into food that other living systems can use. This makes Earth a closed ecological system that doesn't rely on exchange of matter with any other system.
Spacecraft like the ISS are not closed ecological systems. They need to be restocked with food, water, oxygen and other vital supplies. And waste needs to be removed. In the future, if we are to explore other parts of our solar system, we will have to build self-sustaining environments. And to do that, we need to look at why Earth is just right for life.
Well, the main reason is our planet's distance from the sun. Liquid water is a crucial ingredient for life. If a planet is too close to the sun, the temperature is so high that water cannot exist as a liquid. If a planet is too far from the sun, the low temperatures mean that any water will be frozen. Earth is just the right distance from the sun to allow water to exist as liquid on the surface. Earth also has an atmosphere made from gases that provides us with air to breathe and protects us from harmful radiation from space. The mass of a planet and its size determine the strength of the gravity at its surface. If gravity is too weak, any atmospheric gases will escape into space. Earth's gravity is strong enough to hold on to the gases in the atmosphere. Any small planet, like Mercury, will not be able to hold on to the gases. and so will never be capable of supporting life.
Other than gravity, what are the other fundamental necessities for sustaining life on Earth? They are oxygen, water and food.
The most obvious thing that Earth's atmosphere provides for us is air.
It contains roughly 78% nitrogen, 21% oxygen, whilst the remaining 1% is made up of various other gases, including water vapor.
Without this oxygen and water, we wouldn't last long. Before we see how we get these vital ingredients into space, let's take a look at exactly why we need them.
As I run, my body needs more energy to fuel my muscles. This energy is provided by the food we eat. Our digestive system extracts glucose from this food. Glucose is a simple sugar packed with potential energy. To access this energy, our cells have to convert it into the cell's energy currency, the ATP molecule. This is where the amazing properties of oxygen come in. Oxygen drives the conversion of just one glucose molecule into 38 molecules of ATP. So in space, we've got to get the atmosphere just right, or else astronauts will suffer from conditions like hypoxia, the lack of oxygen.
Because we've evolved in an atmosphere of 21% oxygen, we're very sensitive to that percentage. If it goes up too much, we'll begin to struggle, and more importantly, if it goes down too much, we'll start to struggle. So if it goes down a little bit, we'll start to see the responses to hypoxia in the body's attempt to try and maintain oxygen supply to the tissues. Of course, at the extreme end of that continua is anoxia, no oxygen whatsoever, and this is something that happens in situations like drowning or suffocation. Now in that situation, the brain can keep going for just a few minutes using the oxygen that it has at its disposal before it becomes irreversibly damaged. So one of the reasons why controlling our atmosphere in space is so important is because our brain is particularly susceptible to reductions in the oxygen in the environment. Just to give you an example, the brain is 2% of the body weight, but uses 25% of the oxygen the body takes in at rest. So the importance of controlling this environment cannot be overemphasized.
So the management of the atmosphere in a spacecraft has to be carefully controlled. And it's not just the issue of how much oxygen there is. Just like the atmosphere in this enclosed greenhouse, it's also crucial to get the amount of carbon dioxide just right.
The vast number of plants in this greenhouse are quickly using up the carbon dioxide, so the levels of CO2 have to be monitored to make sure the plants have enough of the gas level to keep on growing. In space, it's oxygen that the astronauts need. In fact, since humans breathe out carbon dioxide, astronauts are polluting the air in their own spacecraft as they breathe. And the harder they work, the more they pollute their own air.
Too much CO2 is toxic for us, so spacecraft have systems that scrub it out.
On Earth, plants are natural CO2 scrubbers. They absorb carbon dioxide during photosynthesis, which is how they make their own food using the energy directly from the sun.
In space, it's not so simple. On the ISS, carbon dioxide scrubbers chemically remove excess CO2. These scrubbers use lithium hydroxide powder that reacts with the carbon dioxide to remove the CO2. To manage the removal of carbon dioxide and the supply of oxygen, the atmosphere in spacecraft has to be carefully controlled. On the ISS, oxygen is mainly made from water in a process called electrolysis. Water is split into its component molecules, oxygen and hydrogen, using electricity. Additional oxygen is also supplied from storage tanks carried up to the ISS from resupply spacecraft.
Having been given the go for final approach, the Soyuz now has begun its approach to the docking port of the Zarya control module, now just 111 meters.
Another vital ingredient provided by our atmosphere is water, or H2O. Our atmosphere recycles the water from the Earth's oceans, providing us with this life-giving liquid. Water is needed by our bodies 24 hours a day to keep millions of complex chemical reactions working. It carries nutrients to our cells and it carries waste away. It keeps our temperature regulated and it provides vital lubrications for our joints and our digestive tract. The level of water in our bodies has to be very tightly controlled, and it only takes a small change in our water balance to make us ill. We are expelling water from our bodies all the time. Around 50% of it goes out in urine and solid waste. About 47% is lost through our skin as sweat. The more we sweat, the more water we lose. And this is why, when exercising, it's important to drink water. The rest we lose like this. That's water vapor from my lungs. An average healthy person can lose almost 2.5 liters of water a day. And when you drink less than you expel, your body starts to dry out or dehydrate.
We need fresh water, but 97% of the water on Earth is salt water in the oceans. 2% is trapped as ice. This leaves only 1% available as fresh water. So, how do we get it? The sun's energy heats up the sea, evaporating a tiny amount of it into pure water vapor. This water vapor cools and condenses, forming clouds. When the clouds are fully saturated, the fresh water falls as rain or snow. We call this process precipitation. Wind blows some of these clouds over the land, and that's how it gets into our rivers and lakes, and eventually back into our bodies as fresh water for us to drink.
And so the cycle continues. But things in space are not quite so simple.
À tous de DDO, attention pour le décompte final. Top, allumage Vulcain. Allumage EAP, décollage.
Most of the water on the ISS has to be ferried up from Earth. Since it costs around €20,000 for every liter of water that is shipped into space, a glass of H2O on the ISS is the most expensive cocktail these astronauts will ever drink. And in space, astronauts still need to brush their teeth.
Water is forming with the tension of the surface, almost a perfect sphere. Here you can see a very perfect sphere.
Crew members are allocated 3 liters of water daily. If you compare that to life on Earth, we use at least 50 liters of water just taking our morning shower. So in space, recycling water is essential. Wastewater, condensation, and even urine is recycled into fresh drinking water.
When we journey to distant planets like Mars, we will not be able to resupply the missions from Earth. These long-duration missions require sophisticated methods for making their own oxygen and water, recycle the waste, and even grow their own food. ESA has a number of research projects underway to develop these technologies, one of which is Project Melissa.
Dr. Christophe Lesseur is leading the research program to develop a self-sustaining ecosystem. Melissa has been conceived as a self-sustaining ecosystem intended as a tool to understand artificial ecosystems and for the development of the technology for long-term manned space missions.
Today, the target for a Mars mission is to be able to recycle roughly 40% of the food. Why 40% of the food? Because if you recycle or produce 40% of the food of the crew, directly you produce 100% of oxygen and 100% of the water that the crew will need.
Christophe and his team are developing a prototype system that will consist of 5 separate but interconnected compartments. In the first 3, waste will be progressively broken down by fermentation processes. In the 4th compartment, algae and plants will be grown to produce food, oxygen and water. The fifth compartment will mimic the living quarters of a spacecraft, where the astronauts will consume and recycle the food, water and oxygen produced from the first four compartments, closing the loop of this self-sustaining ecosystem.
There is another criteria which is very important, is the quality of the food you will need to produce. You can fill the requirement in terms of nutrition with wheat only, but you have to consider the acceptance. And if we feed the crew with only wheat, of course we will have probably some difficulties.
The size of Melissa will ultimately depend on the number of astronauts and what they want for dinner. You would need about 10 square meters growing area per person if you want to live on wheat. Far less if you're happy with algae. Once the basic needs of the crew have been met, the next big challenge they face are the complications of weightlessness. Our bodies have evolved to live with the power of Earth's gravitational pull.
Without it, I would experience weightlessness and float around everywhere instead of having to jog. Like me right now, astronauts find the freedom from Earth's gravity exhilarating when in space. But weightlessness also complicates the business of daily life.
Our bodies have evolved to cope with Earth's gravity. Take gravity away and our bodies begin to develop some unique problems.
One of the most visible effects of weightlessness are the puffy faces that astronauts develop in space. On Earth, it is much harder to pump blood up to my head than down to my legs. The heart has to work against gravity. If I keep this up too long, too much blood would flow to my head and not enough to my legs. Quite soon, I would feel pretty awful.
In orbit, astronauts are in a weightless environment. It is just as easy for the heart to pump blood to the head as it is to the legs. And so blood collects in the head and astronauts experience puffy face syndrome, which causes nasal congestion, headaches and other ill effects.
Astronauts' legs also suffer. The legs get less blood and grow thinner.
Our muscles are also affected by weightless conditions. They lose tone and mass, eventually leading to muscular atrophy, the wasting away of muscle. It's use it or lose it, and the same goes for our bones.
We think of bones as rigid pillars. But like muscle, bones are actually dynamic living tissues that constantly reshape themselves in response to the stresses placed on them.
Osteoarchaeologists like Dr. Christopher Knoesel and his team study the effects that different lifestyles had on bones in the past. Here they are looking at the bones of a medieval archer. This research gives valuable insights into the effects of weightlessness in space.
Amongst the things that we know about the medieval period and these soldiers is the longbow was one of their chief weapons, and oftentimes it was the weapon of choice. What's amazing is that, at least in this case, this individual's body has in a sense been shaped by that particular activity because it formed a dominant part of their training from the time they were very, very young. So their body has been altered. It's almost like you can sort of read the activity from the bone. You can see that especially in this region here, this bone, the right side, is much more curved. So it's got more torsion in it. You can actually see that the left one here is a bit broader in this dimension. There's more bone in the left elbow region. What these individual human remains tell us about bone tissue is that it's very, very plastic. It's changeable, malleable, alterable. But importantly as well, it's not just the muscle-bone interaction and movement, it's also weight and gravity. The implications for space travel are over a long period of time. What you will probably see is a lack of density in the bones, simply because the forces aren't acting in the same way on them that they would in an Earth environment.
Normally, two types of bone cells, called osteoblasts and osteoclasts are constantly building and destroying bone material. But in space, the lack of stress on the bones affects the function of these cells, leading to loss of bone mass. So each month in space, an astronaut can lose up to 2% bone mass, as well as suffering from muscle atrophy.
Yes, that's correct.
Separation.
Undocking confirmed at 2:44 p.m. Central Time.
You can imagine that on a 2-year round trip to Mars, this would be very serious if nothing was done about it.
Research into new technologies will help us avoid many of these problems in space.
This young archer is using a modern bow made of lighter, stronger materials, giving it the same power as a 15th century weapon. New technologies have contributed to helping him avoid the physical problems experienced by his ancestors. Similarly, ESA is developing new materials and testing innovative technologies that will one day help astronauts spend long periods of time in a weightless environment without damaging their bodies. Currently, astronauts have to exercise for at least 2 hours a day and eat a careful diet to counter weightlessness effects. But this is only a partial solution. These effects can not only be studied in space, but also on the ground. At MEDES, the French Institute for Space Medicine and Physiology in Toulouse, France, research for ESA is conducted in bed rest experiments.
A bed rest study is a model used to mimic weightlessness on ground. Actually, it induces the same physiological changes as weightlessness. We put the volunteers in head-down tilt position at -6 degrees, and all the activities are done in bed. Shower, eat, watching TV, leisure, everything is done in bed.
The participants in these experiments can spend up to 2 months in bed.
The bed rest studies have 2 aims. The first one is to study physiological changes induced by microgravity. And the second one is to design and test new countermeasures to counteract the effects of weightlessness on the body.
MEDES is currently testing a short-arm centrifuge which could help prevent the negative effects of weightlessness during long-term space missions. The spinning motion of the machine mimics the effects of gravity. The centripetal force on the body could be a way of ensuring a blood pressure gradient and some physical stress on the bones, similar to those on Earth.
It works like a ride in an amusement park because it creates a centrifugal force that recreates the gravity along the body axis.
The idea is that astronauts would spend a short time in the machine every day to counteract the effects of weightlessness. You could call it a trip to the spin gym. Devices like these will be essential if we are to ensure the health of astronauts when we send them on long space missions. We have seen how our bodies have evolved under the pull of Earth's gravity and looked at some of the problems that need to be overcome when we spend long periods in weightlessness. But this is not the whole story.
Assuming that astronauts have plenty of oxygen to breathe, food to eat and water to drink, the next challenge they face during long space missions is less obvious: radiation.
We have evolved to live with protection from the radiation coming from the sun and from outer space. Earth protects us from this lethal radiation in 2 ways. Our atmosphere protects us with a layer of ozone that absorbs 97% of the sun's harmful UV radiation. Fortunately for us, UV radiation is very easily blocked. Most of it can't penetrate ordinary glass or even a thin layer of clothing. This means that in space, UV is not a problem inside the spacecraft, and the astronaut spacesuits protect them from UV when working outside.
However, there are many other different types of radiation coming from space, which can play havoc with the cells in our bodies if we receive large enough doses. This is high energy radiation, mostly composed of X-rays, gamma rays and cosmic rays.
Once again, our planet protects us from this high energy radiation. The Earth's core creates a magnetic shield called the magnetosphere. It surrounds Earth, reflecting most of the incoming charged radiation.
Doses of radiation are measured in units called sieverts. Scientists estimate that the average person on Earth naturally receives 2.5 millisieverts per year.
This level is so low that we can consider it safe. However, a 6-month stay on the space station exposes the crew to the equivalent of about 600 chest X-rays. That is why on the ISS, astronauts' radiation dosage is carefully monitored on a daily basis. A round trip to Mars would expose an astronaut to a dose of radiation that is the equivalent of their lifetime's limit, enough to give them a very high risk of developing cancer. This is clearly unacceptable, and ESA is developing technologies to reduce these risks.
To look at the long-term implications of high radiation exposure, a human-like torso called Matryoshka was fixed to the outside of the ISS in 2004. It is made of natural bone and human tissue-like material.
Continuing with mounting activities for the Matryoshka experiment.
After 1.5 years of exposure, it was brought inside the ISS to measure the radiation there. The results will be used to develop technologies to protect space travelers from radiation during long periods of time in space. We've talked about some of the physical challenges of long-term space exploration, but what about the psychological challenges?
Scientists like Dr. Oliver Angerer are studying the psychological effects of confinement and the implications for long missions in space.
You have a limited number of crew members living together in very small quarters with limited privacy. So any small factor of daily life, certain habits that people have, for example, that you would disregard in a normal terrestrial environment, simply become much more important and can lead to significant conflicts. In the worst case, of course, you can have people really developing severe psychiatric symptoms. It could be a possibility in long-duration spaceflight in the very worst case. This can really be a major danger for mission success.
In Antarctica and Russia, ESA scientists are currently researching the psychological issues that will arise on long-term space missions. In 2009, 6 volunteers will climb through the hatch of a Mars 500 spaceship mock-up and not come out for over 500 days.
Dr. Jennifer Ngo-An is leading the ESA part of the research effort.
The crew members will be locked up with 5 other crew members for a very long time. So they will have to deal with each other, they have to get along, they will have to solve problems, and especially being away from their friends and family will have an impact on the crew members. In order to make the Mars 500 program as close as possible to a real spaceflight mission to Mars, we will introduce a couple of measures that the crew member will not like. Among those are that they will have to eat the food like astronauts on the International Space Station. There will be a communication delay. In the worst case, we are looking at a 20-minute communication delay. In addition, there will be no shower in the facility, so they will have to adapt to the conditions that the program and a real spaceflight mission will have.
As we have seen, there are many challenges to long-term spaceflight. To live there, we have to find ways to supply all of our energy, air and water needs. We need systems that help us survive in very confined environments, and we need ways to guard against the effects of weightlessness, which in the long term can have serious consequences for our health. But our desire to explore has always driven innovation and adaptation, and we've come a long way. In as little as 10,000 years, we have developed technologies that have totally transformed us and the world in which we live. In the last 50 years, we have put man on the moon, and now ESA and its partners have a permanent crew of astronauts on the ISS, where we are preparing to take the next step.
We're only at the beginning of our journey. Who knows where it may lead? Will you be one of the first pioneering explorers on Mars? Or perhaps you'll be one of the many space scientists like me that will help to make it all possible.